So we had left off somewhere in the middle of lesson 4.2. 4.1 was kind of your basics of heats of reactions, and then lesson 4.2 introduces some new ideas. And you should have this written down, so it shouldn't need to take too much. We're talking about things at standard states generally. Non-standard states come later, and there's a formula for converting. But for now, we're working with just standard states, which means we meet all of these conditions, which means that we can use this table that you have in front of your notes, the charts of thermodynamic values. It has 4 columns. You've got a substance, you have delta H, delta G, and S. So the first new thing that comes up is S, and that's actually entropy. Make sure you go back and take a look at it. Entropy is kind of the old way of saying it is how disorganized can something be. And in general, chemistry and the universe favors disorder, like a mess, more than it likes things to be ordered or clean. So kind of like, I remember my high school chemistry teacher saying, you can clean your room and then it gets messy again. And when your mom tells you to clean your room, you can say, well, Mom, it's just the entropy that's causing my room to go back to its natural state. Don't ever say that to your mom, please. That's not very respectful. But that was his little analogy for it. And so entropy is a measure of how disorderly can we make this. Another little word they use is microstates, which is kind of a no-no to say anymore. Don't ask why, it's whatever. But basically, how disordered can something be? How many different arrangements can you have? So like a solid, it's stuck together. You can't change its arrangement very much. A liquid, you can shake it up, that's changing arrangements. A gas, the particles can move all around. There's a lot of places it can be. We read about this, or at least you were assigned to read about this in the textbook, maybe in late November. It wouldn't hurt to go back and skim through it. When entropy is changing, and this is one of our AP formulas, and most of the AP formulas look the same for this unit. Delta S equals the sum of the entropy of all the products minus the sum of all the reactants. That's a pretty typical formula. If it's greater than 0, entropy is going up. It's becoming more disorderly, more of a mess, more possible ways to arrange things. If it's less than 0, less disorderly, basically you're cleaning up your room there. There were ways to increase entropy. You might want to take a look back at this. I don't want to waste your time by talking about all of them again. But these are all the different ways that you can make things more disorderly. Some examples, and this is where we're ready to pick up. So looks like we have just finished example 2. And this next idea is in some ways related to entropy. It's also related to some other pieces that we've talked about in this unit. And the idea here is called Gibbs free energy. So the main idea here, there are 2 processes that really drive thermodynamics. 1, change in enthalpy or decrease in enthalpy, releasing heat. And 2, increase in entropy. So if you're releasing heat and you're making something more disorderly, that's like your best case scenario. not a lot to be written here. That's good. Okay, so we'll go quick through this. So when these two directions take place, when we're decreasing the entropy and, excuse me, two similar words, okay? So when we are decreasing the delta H, so basically making it negative, and we are increasing the entropy, this is the best case scenario. And there's been a lot of terminology changes over the last 15 years. So the way things were when I was in high school are not really supposed to be said anymore because somebody changed the ideas of what should be in a textbook. Did they change what actually happens as far as the chemistry itself? No, they just changed the terminology. And so we have to be kind of careful. I'm going to have you mark a few things out because there's words that AP just does not want to hear. So there's idea number one, it's the bold print. And then there's the sentence right after it. When these two directions take place, right here on the board, the process is said to be thermodynamically favorable. You might underline that. Thermodynamically favorable. And then it has parentheses and says, or spontaneous. If you look at our textbook, which was published within the last 10 years, which is what we're supposed to have, it says spontaneous. If you watch things on Khan Academy, it says spontaneous. If you write the word spontaneous on the AP exam, they're going to give you a big red X. Do not write the word spontaneous for AP. Thermodynamically favorable means it's something that is likely to happen. It has conditions that are right for this reaction to take place. The problem that they have with spontaneous, what does spontaneous mean to us? Like somebody's going crazy or something's just automatically going to happen. It's the automatic thing. Spontaneous makes it sound too automatic, like it's just going to happen no matter what. And sometimes it doesn't. Sometimes you need that activation energy, right? Remember that? So here was the original energy, and then there was a spike to get over, and then, you have to get over this bump, and that's something to think about. And so they really, really hate the word spontaneous now. Every conference that I go to, it's like half of the week they're just saying, don't say spontaneous, don't say spontaneous. Did everybody cross it out? Next sentence, when they are not, the process is thermodynamically unfavorable. You see where it says non-spontaneous? Go ahead and mark that one out too. When a process is non-spontaneous or thermodynamically unfavorable, in the forward direction, it is thermodynamically favorable in the reverse direction. So later on, you might go back and everywhere you see non-spontaneous, put thermodynamically unfavorable. And everywhere you see spontaneous, put thermodynamically favorable. So basically, if the conditions are unfavorable, if you turn the reaction around, then it's a favorable reaction. So if you think about the formation of rust, things just rust, right? That's thermodynamically favorable. Is getting rid of rust easy? No. So if you look at this reaction where rust becomes iron and oxygen, that's a thermodynamically unfavorable reaction. But if you turn the reaction around, it's going to happen. It's going to rust. So Gibbs free energy, there is a formula here, and delta G is Gibbs free energy. or you might just hear it called free energy, is defined as the change in enthalpy minus the temperature times the change in entropy. So there's a chart here. So let's make the chart. All right, so delta H, delta S, and there's another way you can make this chart, and I will show you that at some point. So you have the pluses and the minuses. So first situation, when your delta H is negative and your delta S is positive, we're going to say thermodynamically favorable. I wish there was a shorter way to say this. When delta H is positive, which means it is absorbing heat energy, and delta S is negative, which means things are becoming more orderly, I'm going to shorten this to say unfavorable. And then there's other situations. So negative delta H, that means it's releasing heat energy. But a negative delta S, it's becoming more orderly. It's releasing heat, but it's becoming more orderly. It's going to work sometimes, but not all the time. And so we would say it is thermodynamically favorable but specifically it has to be at low temps. Because there are three pieces to this equation. There's delta H, there's temperature, and there's delta S. So temperature plays a factor. In this case, if the temperatures are low, then it'll work. But if the temperature is too high, it won't work. And then the last one, positive and positive. This is going to work sometimes. Thermodynamically favorable. At high temperatures. So let's take a look at this thermodynamically favorable thing here. Negative delta H and a positive delta S. I just want to look at the signs here. So let's kind of pause here, and we're going to do 4 of these. So here's my delta G. We're going to say our delta H is negative, minus, and here's our T, and our change in entropy is positive. I want to know what's the sign of delta G. Positive. It's negative. We have a negative minus a positive. Not minus a negative, it's minus a positive. And so it ends up, we just ignore temperature because it's always positive. Negative. Best case scenario, delta G is negative or less than 0. So off to the side here, why don't we say delta G is less than 0, when things are thermodynamically favorable all the time. So when things are thermodynamically favorable all the time, these were the conditions: releasing heat, becoming more disordered. But look at the second one, delta G. We have a positive here, minus a negative. This is going to end up being, no matter what, plus a positive, it's going to end up being positive. Or delta G is greater than 0. And then these two down here, of course, the temperature is going to play a factor, because you need to know which one is bigger. Is the number for the delta H bigger, or is the number for the S bigger? And so those ones require a little more work here. But this is the bottom line. Thermodynamically favorable, delta G is going to be negative. When it's unfavorable, it's going to be positive. Do you have room on the back of that page? Is there a blank on the back of that page? Mine is. Maybe mine was. So maybe find somewhere else to write this, and I'll give you a different one of these diagrams. So take a second, find a blank spot. I mean, it doesn't need to be extremely large, but we're going to rewrite this one in the way that I learned it. It's more helpful. So basically, here's how it's going to work. Four boxes. They don't need to be very big. And up here, we're going to put delta H less than 0, which means negative. So everything in this column has a negative delta H. Here, everything in this column has a positive delta H. So left column releasing heat, right column absorbing heat. And we're going to pair that up with delta S. More room here. So delta S greater than 0 for the top row, and delta S less than 0 for the bottom row. What happens when enthalpy is less than 0 and entropy is greater than 0? Look at your other chart.
Delta G is less than 0.
Less than 0. So we'll go ahead and write that. That's good. Delta G is less than 0. What does that mean?
Favorable.
Favorable. Thermodynamically favorable. Specifically at all temps, all temperatures. Doesn't matter what the temperature is, this reaction could happen. How about this box right here where the delta H is positive and the delta S is positive? It works sometimes, right? This one right here, top right box. Positive delta H, positive delta S. This one's pretty specific. It works sometimes, but it has to be at a high temperature. And that's your key. It has to be at a high temperature. When you look at the math of it, you need that second thing, that T delta S, to be a big number so that it can be bigger than the delta H. Let's look at the bottom left box. When delta H is less than 0, so we're releasing heat, that's good. But delta S is less than 0. It's kind of a lot. Releasing heat, but becoming more orderly. It works sometimes. Specifically, yesterday I was thinking that this board is acting up, but it's actually been doing this for years. Specifically at low temperatures. And then your last one, delta H is positive. That means it absorbs heat. Delta S is negative, which means it's becoming more orderly. Does this work ever? No. This one is delta G has to be greater than 0 and thermodynamically unfavorable. If you look back at your textbook, it still says spontaneous and non-spontaneous. Don't go through and cross out spontaneous every time you see it in your textbook. We'll just get a new edition in a few years. So this is just a different way of looking at the same table that we just got. To the left of that table, it has it in bold again. A reaction is spontaneous. Mark out spontaneous. A reaction is thermodynamically favorable when delta G from the reaction is less than 0. And thermodynamically unfavorable when delta G for the reaction is greater than 0. All right, so there's a note here. T is a temperature in Kelvin. It has to be in Kelvin. And we've mentioned this before, and I talked about the temperature scales a while back. T has to be in Kelvin. It doesn't work with Celsius. It's going to throw your numbers way off. It's not built for Celsius. You'd have to do conversions first. Remember, if you have Celsius, add 273, that gives you Kelvin. So if you're 0 degrees Celsius, 273 Kelvin. If you're at 100 degrees Celsius, that's 373. Make sure you do that. That's going to be important. It will really, really change the math if you use Celsius. Another thing to note that it says here, delta G and delta H usually come in kilojoules. Entropy, S, comes in joules. You're going to have to convert it. So whenever you're using this equation, you'll end up with kilojoules minus joules. So you'll need to change that last thing to be kilojoules. It's just one of those things that nobody's ever done anything about. If you look carefully at the chart of thermodynamic values at the top, it gives you the units that they have. And it might actually on the AP formula sheet. I haven't looked at it in a while. Kilojoules, kilojoules, joules. And I guess I don't want to insult anybody's intelligence, but in case you have forgotten This is the conversion from joules to kilojoules. All right, let's move on. So this next thing, idea number 2, this came up in the reading that you may or may not have done about a month ago. Gibbs free energy is a state function. Does anybody know what a state function is? I'm going to give you as simple as I can, and it's not on here. Let's say we have a graph, and whatever this graph is going to be a state function, okay? We want to go from here to here. This is going to be a state function. It doesn't matter how I get here. I can go this way. That's probably the shortest route, right? Between 2 points, a straight line. It doesn't matter if it goes like this. I still got from here to here. It's almost like driving home. It doesn't matter if you drive all the way to Delphi and then to your house, or if you just drive straight home from school to your house. You were here, then you're at your house, right? That's basically what a state function means. Basically, we don't care about any of this stuff in the middle. We just know that we went from here to here. That's a state function. And that is a highly scientific picture that I just drew. It's art. So it's a state function, which means there's a bunch of different ways you can find it. What else is a state function? Delta H. Remember our energy graphs? They a lot of times looked something like this. That was a state function. We went from here to here. There's a bunch of formulas here. So the first one, delta G equals delta H minus T delta S. That's the one that I showed you already. It's on the AP formula sheet. Next one, delta G for the reaction equals the sum of the products minus the sum of the reactants. That's on your AP formula sheet. The next one, Hess's law. Remember Hess's law? This is the thing that gave everybody real trouble in the lab. A quick review on Hess's law. So basically you have, let's say we have two reactions and A plus B yields AB, and we'll say, I don't know, A plus B yields A2B. I don't know, I'm making this up. And so you've got maybe a delta H here where it's negative 10, and maybe your delta H here is, let's say, negative 20. Again, I'm making all this stuff up. And you're trying to find the overall reaction. Remember we had a question with carbon graphite, carbon diamond. That's the idea here. Basically, you're adding these reactions together. And we would probably flip one of them, get things to cancel. And I apologize because this particular example makes no sense, but it's off the top of my head. It's basically where you add two reactions with a known delta H or a known delta G. Much time do we have? About 10 minutes. All right, so we're going to do example 3, and then that'll probably be it for the day. We'll end up running out of time. Consider the following process at 25 degrees Celsius. 2 SO2 gas plus O2 gas yields 2SO3 gas. So we're going to do it A, B, and C, all three of the methods that it just talked about. So the first one, we're going to use, let me duplicate this. First one, this formula. This is the way to calculate free energy when we know a couple other things. We know the change in the entropy, we know the change in the enthalpy, and we know the temperature. It gives us some values. It says delta H equals negative 198 kilojoules per mole. And I'm going to keep my units in here just so we can be careful until you get the hang of it at the very least. Minus, and the temperature was 25 degrees Celsius. It needs to be in Kelvin. 298. And then my delta S, it gives me that one too. Negative 187 joules per mole per Kelvin. Whenever I'm putting units in these things, I like to cancel them out as fast as I can, so I don't have to write it in the next line. Kelvin, gone. And then this joules here, this is where we have to convert. Because this one's in kilojoules, this needs to be in kilojoules. I'm going to go ahead and change it now. And now my units everywhere are in terms of kilojoules per mole. Just get it out of the way right now. So when we do this, minus, I'm going to go ahead and put all of this in my calculator. I find it, here it is. Minus, and this is negative 55.7 kilojoules per mole. Check my notes. So here's what we're doing. We have a negative minus a negative. And if you think back to like 7th grade, that means plus a positive. Negative 198 and 55.7. Negative 142. Yeah, we'll stick with 3 snippet figures. And that's kilojoules per mole. This formula is pretty much plug and play. It's not really too complex. The only thing to remember, make sure you do your kilojoules conversion at the last term. All right. Questions on that one? Everybody's good? Let's move on to part B. In part B, we have the same reaction. Calculate the value of delta G for the reaction given the following. Says delta G, not F, it looks like this. This little degree sign means standard. Standard free energy of this little F means formation. Not super important. It's what it is on your table. Anyway, we're looking for delta G given the formulas, given the numbers that we have. Whenever they give you values for individual substances, and for this one it's negative 300 for that one, it's negative 371 for this one. When you start getting individual chemicals, this is where you know you're going to use the products minus reactants formula. It's one of those AP formulas. It's a pretty simple one, really. So first off, the sum of all the products we have, so there's negative 371, but we have to multiply it by its coefficient. So 2 times negative 371 kilojoules per mole. That's the SO3. Minus, and then all of the reactants. So the first thing we have is coefficient of 2 times, and the value was negative 300 kilojoules per mole, plus, because this sigma here means adding them together. The oxygen has a coefficient of 1, and what's its delta G? You could open this up and look at it.
0.
0, yeah. So you can look it up if you had to, but AP's not going to give it to you, and you can expect it on the test. If it's an element in its standard state, like oxygen gas at 25 degrees, it's 0, which really means that you can just keep that out of the whole calculation. Put the whole thing in your calculator. And we get delta G equals negative 142 kilojoules per mole. It's the same answer we got last time, right? 2 different ways. See what time it is. We've got 2 minutes. Does anybody have any pressing SRT issues? Because I think if we go like 2 or 3 or 4 minutes over, we can get this done. Everybody's good? Okay. Part C, calculate delta G given these 3 reactions. So reaction 1, yours is already written down, so that's going to be convenient. So it looks vaguely familiar, right? Where you have multiple reactions and multiple values. And basically what happens is we want to get it back to that original equation that we had. 2SO2 plus O2 yields 2SO3. And I'm going to go the quick way so we don't take up too much of your time here. We're going to reverse reaction number 1. And so it's going to flip the equation. It's also going to change the sign of the delta G. It's positive. Number 2, we're going to reverse it and we're going to double it. So we change the sign and we multiply the delta G by 2 because we doubled everything. And double number 3. Which means we have to double the delta G for reaction 3. It comes out to negative 1312. And these are the 3 that we add together. Remember, we're canceling things out, so let me change colors. Red. So let's see here. Those. See 3 of these and 1 of these. And basically what you want left over is the original reaction that we were looking for. 2SO2 plus O2 yields 2SO3. The delta G for this reaction, now all we have to do is add these 3 numbers together. And we end up with negative 142. That's the short version of it. So you're probably going to have questions as we actually do these. Don't keep your questions to yourself. Make sure you're asking. Talk to your classmates, talk to me. One of us will help you.